Previously.
I am not particularly liking this data arrangement, to be perfectly honest, these vectors. Generally speaking, so we have 72.1 nanoseconds per iteration to solve all three problems. Hey, look at that! We can do about 9 times faster than our previous implementation. I think that's quite a bit.
Hey boys and girls, welcome back to Fastware. So today we have a second attempt at practicing with the problem that we did a couple of days ago. So this is that magic square problem where rows, columns, and diagonals must add up to exactly the same number. And we had our previous attempt, which I implemented and kind of a summarize that I don't particularly like how the input data is structured and how we actually loop and iterate over that data, consuming the sums. Me, that's kind of it was my first attempt, and I don't particularly like it. I think it can be done much better ways. So let's start with that. We have a struct. We have a problem t. And here we'll have a vector of the int64t. Right, this is going to be our data. Now we will put it in one array, and then we'll be indexing it ourselves rather than having two indexes, or having two-dimensional array and having to index in those two. So we know how the data will be arranged in memory. You'll have everything in a flat one array. All the data will be nice and close together. So it's also going to be nice and hot in the cache. And I like that. So what I'm going to do is now we're going to have an int 32, which is going to be dimension. So we will say that this is like 3 for 3 by 3 and 4 by 4 by 4 and so on, so on. Right. So then we'll have a bool, not book, bool expected. This is going to be our data. Now let's take this and we'll have a, here we go, we have a problem. I'll have an array of these. One thing that we can do would be fairly simple to do, since we now have a dimension for it. We would be able to quite easily optimize for small sizes. So how will we do that? So we can start by doing a switch. So here we have a dimension, and here we have our cases. So for cases 0 and 1, return true. Say, yay, we're done. Now for 2, it'll be a bit more complicated. So we need to add up rows, add up columns, and 2 diagonals. Right? So this is how we're gonna go about it. This is probably a perfect time for us to use binary operations, because we can actually perform something. We actually can perform all these checks in a single go. So we don't need to do many if statements and whatnot. So we're relying on bit manipulation or bit masking here to actually figure out if all of these are the same. And can you think of an operation which, given two numbers and grouping them together with some binary operation, will give you the same number and nothing else? So I will tell you now, I'm going to be using an AND. The way I'm going to be doing this, I'm going to say I want to return. I'm going to say row 2 and column 1 and column 2 and diag1 and diag2. So we ANDing all of them, and then we saying is equal to row 1. So if all of these are exactly the same, ANDing them all together will produce exactly the same number. But if one of them is different, so the bit placement will be completely different from what it was before, and therefore it won't match with the row 1. So this is very simple way of actually doing these checks. Okay, so let's copy this for 2 and apply exactly the same logic for 3 and 4. And here we go. I think our solution for small sizes are implemented as it is. The only thing to do is to check the performance of it. Hey, look at that! We can do about 10 times faster, well, 9 times faster than our previous implementation. I think that's quite a bit. So, the only thing remaining is to implement a generic solution, and we can actually just boop it as well, since there is no need for you to wait for that. I'll see you after that. And are you happy that it was done just so quickly? So to walk past, first we read first row, first column, and first diagonal by iterating over rows, input.I, and then I times that number of dimensions. So let's say 4, would go 0, 4, 8, 12, which is the first column. And then that 4 plus another I, so it will go 0, 5, and what, 0, 5, and in a diagonal. So 0, 5, 10, 15, right? Like that. So we'll compare that, we'll set to result, then we will start all the other rows and columns, and we'll finish with the last diagonal. Standard implementation, and here we go. Since this is one of our special sizes, 3 or 4, we're still running our fast implementations, but we can comment this out to see if our implementation does the right thing, first of all. Go. Yeah, it does the right thing as expected. And we can also the performance of it. Hey, so it's not that bad. So this one is about what, 69, 70. And this one is about 20 nanoseconds. So we can do about, what, 3.5 times faster than our naive implementation, with a bit of thought how we actually group data and access that data. Obviously, the most important thing here is that instead of having two-dimensional arrays, we have actually a single input, which is close together. Therefore, if you think about it, we have int64 for the largest size, where we have case 4, right? That's 128 bytes. That's 2 cache lines filled the brim with data that can be accessed directly. So we're not wasting anything here. If it would be two-dimensional arrays, we would have to index other parts of data, which will be difficult to find. So we have actually implemented something that we can be a little proud. We followed the examples, how matrix manipulation is implemented in something like GLM, or how actually compression is implemented in gzip or something like that, manually unrolling and unwinding loops to actually make the most of our hardware. So we don't have to pay overhead for loops and loop headers and whatnot. We just manually unwind everything in order to get the possible outcome. So I hope you enjoyed. If you did, please leave that like. Subscribe as always, as it helps me out, helps the channel grow. And have fun writing fast code. Cheers. Bye.